All right, in this video, I'm going to go over number 3 from the Unit 6 free response questions. Now, this question is actually called an investigative task. So this is an example of kind of extending the knowledge that you guys have about this unit on inference with means, and we'll get into more about investigative tasks when we start reviewing for the AP exam in April, okay? All right, so there's a lot going on here. Hopefully you've read what's happening in this question. The first question, part A, says to provide this 95% confidence interval and be sure to interpret it. So whenever I see to run a confidence interval, I'm going to be thinking my acronym ACMAC, all right, ACMC, which stands for assumptions, conditions, mechanics, and conclusion. So my first assumption that I'm going to do is I'm going to assume that one person's cholesterol level, or you could say their reduction in cholesterol, that's the whole point of using this new drug, won't affect others. Okay. Then it does mention it is a random sample of 50 people. So this is a random sample of 50 people. Okay. And then to do the 10% condition, right, if I do n times 10 equals 500, it says the population is people with high cholesterol. So it doesn't say like the United States or the state of Texas, or I have no idea what their population is, but I'm going to assume this is the United States. So there are more than 500 people in the US with high cholesterol. So 50 is not too large. Now, the next statement I'm going to do is I need to assume that if I did have the reduction in cholesterol levels from the entire population, if they were all to take this new drug, and I made a histogram of those reductions, I would see a histogram that is normal. I'm going to say the population histogram of cholesterol reduction is normal. Now, they don't give me the 50 data values in terms of the reduction in cholesterol level with this sample, so I'm not able to make a histogram to check this. So I am going to mention, though, that 50 people is larger than 30. So 50 is a large enough sample. All right, so now I'm going to say the conditions have been satisfied. So I will use a T model with 49 degrees of freedom to run a one sample T interval. All right, so I'm going to write down the stuff that I know because they actually gave me some statistics here. So I know my sample size is 50. My degrees of freedom is 49. My Y bar, which is our sample mean, the sample mean reduction in cholesterol is 24 milligrams per deciliter. So 24 milligrams per deciliter. And then the standard deviation is 15 milligrams per deciliter. Here's my formula, Y bar plus or minus T star with 49 degrees of freedom times the standard error of Y bar. And that standard error of Y bar formula is S over the square root of N. Okay, plug in what we know. We know this is 24. We don't know T star yet. I will find it in a moment. Times my standard deviation of 15 over the square root of 50. All right, let's go into the calculator to find that T star. Remember, if you were to draw a 95% confidence interval, how much would I have in each tail? I have to split 5% to get 2.5%. So going to my calculator to find my T star, I'm going to do second vars, number 4, which is inverse T, and the area is 0.025. Degrees of freedom is 49, and that will give me my T star of essentially 2.01. Okay, so then I can go into my calculator to run the actual function here, which go over to test, stat over to test. This is a one sample T interval, so number 8. I'm going to use statistics here because that's what I have. My average is 24 milligrams per deciliter. My standard deviation is 15 milligrams per deciliter. There's 50 of these people, and we're doing 95% confidence. So my answer is going to be 19.7 to 28.3. So 19.7 to 28.3. Remember to leave that little space to do a line where you can write down the margin of error. All right. So when I write down the margin of error, the way I do that is I subtract 24 minus 19.7, which will give me the margin of error of approximately 4.3 milligrams per deciliter. Okay, so once I finish with this, I'm ready to write my statement. I am 95% confident that the mean reduction in cholesterol for the new drug in the population of people with high cholesterol is between 19.7 and 28.3 milligrams per deciliter. All right, so that is part A. Okay, now as you might notice, right, that usually is like one question on a traditional AP style FRQ, but you can see that this is just part A of multiple parts. So the investigative task is going to be more time, right? It's going to take you more like 20 to 30 minutes as opposed to 10 to 15 minutes. Okay, so part B, it says that they decided, I should have mentioned in the first part here, it says if the company is hoping to see that the average reduction is more than 20 milligrams per deciliter, then they will go ahead and start basically producing this on a wider scale. But if you look in the interval here, right, the interval we made, 20 is in there, so we cannot reject 20. So this interval would not be enough evidence to say, you know what, you can go ahead and think that it's more than 20 on average for the reduction. So the company is probably not going to produce this drug, at least at this time. So part B then, they're not convinced that this new drug is better, even though it looks like it is. Statistically, it's not significant enough for them to decide to invest all this money. So they're going to run a test, and they run this test with these hypotheses. And they get a p-value of 0.033. And because that p-value is less than their alpha level of 0.05, they're going to reject 20 in favor that the new mean is above 20 on average. So they're going to go ahead and start making the drug. So the question is, why the difference, right? Why with the interval, we see 20 in the interval, so we can't reject it. But then when they run the test, they end up actually rejecting 20. So there's a couple ways to answer this. The first way that I answered it was, if I were to run a confidence interval that links with this test, right? So if I were to make my T model, right? The idea is that if they use an alpha level of 0.05 and it's a one-tailed test, then the idea is that you really have like 5% here, 5% here. So that would be a confidence level of 90%. So really to link this, they would need to run a 90% confidence interval. But if you look at what we did in part A, we ran a 95% confidence interval. So that technically is not actually kind of doing the same thing. So that's one way to answer it, right? Another way to answer it is that when you're thinking about the fact that this was a one-tailed test that gave us a p-value of 0.033, if I wanted to make this correct and do 95% like I did in part A, that's really 0.025 in each tail. So a one-tailed test would mean that you would actually use an alpha level of 0.025 if you want to do this right. And if you look at that p-value of 0.033 compared to that p-value is actually above that alpha level. So you actually would get the same conclusion. So that's one kind of way to do it. Both of those are very similar. So I'm going to try to summarize that in words for you. All right, so let's see. If I wanted to run an appropriate one-tailed test that links with the 95% confidence interval, I would use an alpha level of 0.025. All right. And if I use an alpha level of 0.025, basically that p-value of 0.033 being above my alpha level of 0.025 would actually lead me to the same conclusion as part A, where you're not able to reject 20. All right, so a couple ways to try to explain part B. Okay, part C. The company would like to determine a value L that would allow them to make the following statement. They're 95% confident, so let's see, 95% confident that the true mean reduction in cholesterol level is greater than L. So if this is L, right, whatever this is, if this is L, and you can notice in this formula that it's essentially the same formula we used in part A, but it says only subtraction, so they're just doing the kind of lower part of the interval. So then the idea is that there would be 95% that way, and so how much is in this tail would be 5%, which is different than when we found a T star up here, right? We had 2.5% in each of these tails when we did part A. So we will actually need to get a different T star, right? It requires a different critical value to get that letter L. So I'll go ahead and do the same kind of stuff that we had before, which was I'll do y bar. This is L equals y bar minus, I need to find a T star with 49 degrees of freedom times, it does give me that formula, S over the square root of N. So if I go to my calculator, turn it on, hit second vars, number 4, and again, change this to 0.05. That's different than part A. Same degrees of freedom. So I get 1.677. So it's going to be 24 minus 1.677. I use the rounded one there, but when I calculate this, I will use the not rounded one. And it was 15 over the square root of 50. All right, so if I do this, I'm going to multiply this by 15. Oh, wait, hold on, sorry. Let's do this right. So let's do 15 divided by the square root of 50. And then that times that critical value. I'm going to leave it as a negative because it's going to make a subtraction. And then I'm just going to do 24 plus that, which again is really 24 minus the 3. So if I do this plus 24, I'll get my low number, which is 20.44. Now you can see that comparing this to part A, where my lower part of the interval was 19.7, this lower part of 20.44 is actually now above that average reduction of 20. So part D is essentially asking, would they have a different conclusion then? So it says, if they'd use this, right, 20.44 milligrams per deciliter as their lower part of the confidence interval in part C, in part A, rather than 19.7, would they have reached a different conclusion? The answer is yes, because 20 milligrams per deciliter would not be in the confidence interval. So the company would conclude the average reduction in cholesterol using the new drug is above 20 milligrams per deciliter. All right, guys, so you can see that this was a lot longer, a lot more parts, a lot more thinking. It's just in general, the investigative test is going to be more challenging than a traditional FRQ. So we'll practice some of these as we get closer to the exam date. All right, good luck.